In this video, we're talking estimating a population proportion. It's confidence intervals, but one particular kind of confidence intervals. These intervals which are best guess for a population proportion, which is just a fancy word to say percentage. Now look, we'll talk about some components, some things to check before you start even building these confidence intervals, because we don't want to build our intervals based on some bad information or maybe some information that it doesn't completely capture the group. We'll go through some applications and maybe sometimes where confidence intervals work and sometimes where they don't work. So it's important to understand, again, the limitations of these confidence intervals. Without further delay, let's dive in. Previously, we talked about this population proportion, this 26% claim of Gen Z users use their smartphone 10 or more hours a day. They said, look, it's a 95% confidence interval, which means, again, that the population may be nowhere inside of this interval value. But I know what you're hearing. You're saying interval value, that's just one. But again, that's misleading because all of these confidence intervals, they should have a swing or margin of error, this epsilon character. In this case, it was 3.1%. And so really this 26% is misleading because really it can be minus that 3.1%, in which case you'd end up with 22.9%. And then if I add, I'll end up with 29.1%. And one of the big issues that we run into is the population proportion could be as low as 22, it could be as high as 29, and it can be anywhere in between. And so if you're asking then, why did they pick this number 26 to proclaim or put out there? Well, they're just hedging their bets because that 26% is in the middle. So if it's on the high end, they don't look too embarrassed. And if it's on the low end, again, they don't look as embarrassed. But it is no more likely to be 26% than it is to be, again, 23%, let's say. And so the picture for this confidence interval, well, here's a picture over here to kind of zoom in on here in a second, that for these population proportions, their normal distribution, which is why we have this normal distribution curve, this bell-shaped graph, where 95% of the confidence intervals that I generate, again, this 95% may look like a probability, but that's not quite accurate as we talked about previously. Then when we talk about 95% confidence, it means that this interval, the 22 to 29, that 95% of intervals built in this way will contain the mean somewhere. Again, maybe up here, maybe down here, hey, maybe in between, but we're not sure. And so again, we need to understand the limitations, the level of confidence, yes, and the margin of error as well. In this section, we're actually going to go through, okay, how did these confidence intervals actually get built? We'll do a little bit of Excel, and I'll open up Excel certainly as we progress. But our big limitation is, again, I don't know what the population proportion is. And so we have to get the next best thing, which we often called our point estimate. I'll underline here is our sample proportion, phat. Before we get into building these, though, we need to check, because just because we have a sample doesn't automatically mean that the sample proportion is normally distributed. Again, it really depends on that sample and particularly what size it is. So let's get into it. So when we talk about this sample proportion, it's important to understand it is a random variable. On one sample, I may get a sample proportion of 26%, like the example I did earlier, but another day, I may get a sample proportion of 25%. Ideally, all these numbers are relatively close, so I shouldn't randomly sample and get 50%. In order to have a proper sampling distribution for the sample proportion, and again, the big check is we want normal distribution. Well, there's really two quantities that I need to multiply together. The first one is n, how big is your sample, times the sample proportion, people answering in the way that you wanted them to, has to be greater than or equal to 10. But also the converse has to be true, that the size times 1 minus p has to also be greater than or equal to 10. Both of those have to be true at the same time. If not, then your sample was not large enough. We'll see some examples here in a minute. Very important. You must check. This really comes from this idea that n, your sample, has to be sufficiently large. You'll remember for much of the time, especially when we talk about sample mean, oftentimes n greater than or equal to 30 is fine for sufficiently large. We call that the central limit theorem. For proportions, though, it's quite a bit different, because these proportions, again, say can be something as small as 1%. Well, if only 1% of people are responding in the way that you're interested in, if you talk to 30 people, it's not likely you're going to get a single person reporting or agreeing with your proportion, what you're interested in. because again, 1% of 30 is 0.3 of a person. And so ultimately, it depends on your sample proportion, but you may have to have even larger sample sizes to capture at least one response, or at least, in this case, 10 responses, either for or against what you're interested in, which is where that 10 number comes from. I'll tell you, it depends on different textbooks. Some textbooks require this number to be 15, but for us, we'll stick with a nice even 10. Once we have normal distribution, the mean of the sample proportions is given by this mu sub p hat. This was when we introduced sampling distributions earlier. And the standard deviation, underline here, has a nice little square root formula. So again, a very important check. In fact, let's look at some examples checking exactly that. Is it even proper to build a confidence interval for the population proportion? Let's get into the first example. Determine if a confidence interval for a true population proportion P can be constructed for the following scenarios. We'll circle and then justify our response. First one, you randomly sample 45 individuals and find a sample proportion P out to be 0.82 or 82%. And they say that they support mandatory quarantines of anyone who had been in contact with an Ebola patient. Interesting. Okay, 82%, 45 people. Can we somehow take this information, again, maybe this is like for one small town or something, can I take this information and apply it to the bigger population group? Before you start building confidence intervals, you need to check. And it's those two quantities we talked about earlier. The n times p has to be greater than or equal to 10. Again, we're not sure yet. And n times 1 minus p has to be greater than or equal to 10. For the first one, n is my sample size. I talked to 45 individuals here, which is a decent number. Maybe it's large enough, we'll see. Any times my sample proportion, these things should have hats on them. That should be 0.82. This should give a nice number. I cheated. I did it beforehand. If you multiply these two together, you should get 36.9, which, again, question, not sure. Is it greater than or equal to 10? You betcha it is. Yes. So far, so good. For the next one, that should be n times 1 minus 0.82. And again, it's a question. We're not sure. Is it greater than or equal to 10? We can multiply that out. I should have 45 for my sample size times 1 minus 0.82 is going to be 0.18. We're going to get 8.1. The butter. Greater than or equal to 10. I'm thinking no siree. So can I build this confidence interval? No, I cannot do a confidence interval for the true population proportion. So really what that means is oftentimes when we hear sample proportions, we understand, okay, look, it comes with a grain of salt because this is just the one sample I talked to. But confidence intervals allow us to take that guess and then apply it to a bigger group. In this case, I cannot apply it because I didn't even capture a large enough audience to really tell. In this case, it looks like 8 of my 45 people said that they're not interested in. And so I didn't capture enough of both sides in order to warrant an application. If I up that sample size, well, maybe I can get a better picture, but certainly this sample proportion should be treated as a random statistic, anecdotal at best. Let's look at the next one. For a randomly selected group of 90 adults, 34 can tie an alpine knot with paracord rope. Let's look and see, check. Can I somehow apply this anecdotal case, this proportion, onto a larger group? Again, the classic check is n times p hat greater than or equal to 10 and n times 1 minus p hat greater than or equal to 10. I'm missing one thing here, and it's kind of important. I should have a p hat. Currently, I don't have one. If you'll remember, the formula for p hat is x divided by n, x number of people doing what we want them to do. In this case, that is 34 people doing what we want them to do, divided by 90. We can do this as a proportion here pretty quickly. That should be 0.3, and then a lot of sevens repeating. I'll just write 3 sevens to meet 4 decimal places. Check it out. So over here, make sure I'm writing the way, for n, my sample size, I talked to 90 adults, and my sample proportion, you could write as 0.3777, but instead, let me just write the fraction that we wrote earlier, this 34 divided by 90 business. And again, it's a question, we're not sure, is it greater than 10? The reason why I like the fraction why it's friendly is look at those 90s, they cancel out, and we end up with a nice, very friendly multiplication of just, product of 34. And you betcha, yes, this does satisfy that condition. Next up, more friendly, I should get n times 1 minus p hat. And so if I keep these, it should be my sample size is 90. I'll then get 1 minus 34 divided by 90, greater than or equal to 10. We're not sure. Again, if you'd like, you can do it in your calculator. You need to do this fancy arithmetic here. If you want to subtract these, you need them both to be fractions. So technically, this should be 90 over 90. And then you can subtract the numerators. Anywho, this will be 90 on the outside, and it should be 56 divided by 90 on the inside. Still a question. Maybe we're not sure. Greater than or equal to 10. Just like before, these 90s cancel, and you should be left with just enough space. 56, which you betcha, yes, is greater than 10, which is good. Both of these conditions are satisfied. I can go over here. Yes, this is a good enough sample. I can do a confidence interval for the population P. And so a little bit of a less of a grain of salt. Again, the first one I couldn't do anything with. I can't build a confidence interval from it. And again, this should be taken as anecdotal, not applicable whatsoever. But for my larger group, my 90 adults and my 34 people who can tie an alpine knot, this 37% can be taken with a bit more weight associated with. This is a good best guess, or we often call those things point estimates. And then it's with that we can build a proper interval. And so it's something we need to be aware of. Check, make sure you can actually perform the confidence interval, then we can actually get into building it. Speaking of which, how do we build these confidence intervals? We're going to use something called a Z interval. If you're curious, whenever you see a Z, all this means is that this is a standard, normal distribution. It has to do with the way this is built. In fact, I'll bring that up in just a minute. In order to build these intervals, you need 3 ingredients, but those ingredients sometimes can look differently. So for instance, you need either a sample proportion or a number of people doing what you want them to do. Okay, you're going to need at least one of those two. And then you're guaranteed always going to need a sample size, and you're going to need a level of guarantee or a confidence percentage. How confident are you in your interval? How do we use those ingredients? So all confidence intervals need 2 things. They need the best guess, a point estimate, in which case sometimes you just straight have it, p hat, and they need a margin of error swing, how wide that interval going to be. So really the only thing we need to compute is the margin of error. There are 2 ways to compute it. I will circle, I will highlight, I will star. This is the one that I would encourage you to rely on. There is a way to do it, quote unquote, by hand using a little bit of multiplication. I have it over here. There's this thing called a critical value, this Z alpha over 2. If we talk about, for instance, a confidence level of, let's say 95%, and if down over here, we have a table here which gives you different critical values based on your level of confidence. If I have a beta of 95%, then I have a critical value, is Z alpha over 2 of, I'll write it up top, 1.96. And that's where that critical value comes from. So not terrible to compute. And again, this table is readily available. If we look at the standard deviation over here, this is the standard deviation of the sample proportions. Here's your formula. And so if you simply multiply those 2 ingredients together, the critical value, which you pull from the level of confidence, and we also call this thing the standard error. It's a little bit more jargon for you. If you multiply those 2 ingredients together, you will get the margin of error. But don't work harder than you need to. Instead, Excel can do this very quickly. If we simply use the function confidence.norm and we apply 3 ingredients, the first one is 1 minus beta. This is technically alpha, or as I'll show you, I'll just write 1 minus 0.95. The second ingredient is kind of like the standard deviation, but it's without the sample proportion. That formula is right over here. It's the square root of p hat times 1 minus p hat. And then the last third ingredient, here it is the sample size. So if you can just type in those 3 ingredients, boom, you'll get your margin of error. And once I have the margin of error, then I can build both my left and my right endpoints by subtracting and adding that level of confidence. To put everything into perspective here, this is kind of what you can expect to see. That look, you have 2 ways to compute these confidence intervals. That either you can plus or minus this critical value times the standard error, or, working too hard in my opinion, here's a nice little function to do it, confidence.norm. Let's actually get into some examples, see how this is actually built. Policymakers want to estimate the population of New York adults who favor a mandatory quarantine of anyone who has been in contact with an Ebola patient. Hopefully they'll talk to more than 45 individuals like we talked about earlier. They hire a private firm to construct a 95% confidence interval for the true population proportion. The firm randomly samples 1,050 New York adults and finds that 861 favor the mandatory quarantine. So again, classic New York's like, look, we don't want to maybe take an unpopular opinion, and so instead can we just pay a firm to kind of get what the popular consensus is, and we'll just do that, right? Wash our hands of this and say it's what the people want. How can we build this confidence interval? Again, it's us playing the role of the firm. Well, the first point is that we need to find out what the point estimate is. What is the current best guess? And I have the formula written in blue for us here. It should be that p hat is always x divided by n, x the number of people doing what, in this case, we want them to do. It looks like 861 of them divided by my sample size, 1,050 as a decimal. You can do that, you can calculate and verify. You should get 0.82, or if you want to write that as a percentage, you can, as 82%. And so that's their point estimate, their best guess. Or is it? Because before we say this is even representative of the larger group of the population, we should verify that this sample is even worthwhile. Is that sample proportion approximately normally distributed? This is that check that we talked about earlier, the n times p greater than or equal to 10, and also n times 1 minus p is greater than or equal to 10. To skip to it is approximately normal. Again, if this was a no, well then, hey, stop the question, you're done. There's no real inference you can build. Before we build that confidence interval, though, we need to understand the limitations of this sample proportion. Here's an example. Can policymakers infer that 82% of all New York adults favor mandatory quarantines? Right? Can the firm just preemptively go, look, the math is too hard for us. Here's that sample information that we gathered. And can the policymakers then go, yep, this is what the whole state thinks? Well, the short answer is no. No, definitely not. Cannot make that inference. And the whole point is, again, this sample proportion p hat equal to 82% should be close, all right, little wavy signs, should be close to the population proportion. But again, we don't know exactly what it is. I know it'd be close, but I'm not sure how close. In fact, it's not until we build a confidence interval that I can even give you a range of values. For all we know, again, at this point, the actual proportion could be as high as 90%. It could be as low as 10%. I have no idea what it is. Because again, what do we mean by close? There's no measurement on that close. It doesn't say plus or minus 2 points or 1 point. And so we have no idea what closeness means. So no, we can't claim that 82% of all, that's population stuff. I only have sample. It's not until I do the normal distribution curve that I can then properly project how close the population proportion is likely to be. Speaking of that confidence interval, let's build it. I have a nice reference for us for that function. Also pull up Excel here in a minute. The first task, compute the margin of error. Let me really quickly pull up Excel, and then we can actually calculate the margin of error inside of Excel. Let me see if I can move over to the right-hand side. Looking at the margin of error, which is that fancy epsilon character, it looks like I should be using confidence. So, all right, confidence. As you type, you'll see it will recommend confidence.norm, confidence.t, confidence, and then the other one down below. We want to do .norm because we're doing normal distribution. And I should have a couple inputs. Again, Excel will recommend, it says alpha, that's 1 minus beta. So I'll write 1 minus 0.95, comma, or you can type in 0.05. For the standard deviation, the formula is written there for us. I can't quite just do or write a square root sign, and so I'll have to type it. But if you'd like to just write square root, you're more than welcome to. I'll write squirt for square root. And it looks for the sample proportion, p hat, which we calculated earlier was 0.82 times, I need 1 minus. So I'll do 1 minus 0.82. Or if you want to be super fancy, you could simply write 0.18. Whew! All right, we're almost there. We have the first two parts done. 1 minus beta, our square root business. And the last and most friendly ingredient is n, our sample size. And we talked to 1,050 New York adults. Ooh, and look at the draw, look at that. We barely fit it in to one cell. And so I'm going to hit enter. It should calculate, no problem. Look at this. This is your wiggle room. I'll type it down below for our reference. There we go. So this is the margin of error. This is the wiggle room that we have. Let me bold it a bit more so we can see it. 0.02324. That's our wiggle room. If you want to think about that as a percent, you can do so. In fact, let me copy and paste just the value over here. And then if I scroll up top, you can see I can just click percent and it'll make it into a percentage. I can move the decimals over a bit more and get more decimal places. But this is E, my error. So I'll write equals E for my error there. So that way we can better conceptualize what our swing is. So remember, we had 82% was our middle of the road, our best guess, point estimate. And then we have plus or minus this 2.3%. So when we're actually figuring out our confidence interval, we have a left and a right endpoint. Now look, our p hat was equal to 0.82, and that was an exact number, so there's no need to adjust it. That was my middle, my best guess. So when I'm building, my left should be p hat minus my margin of error. And then for my right, I should have p hat plus my margin of error. And so putting these two together, I'll use cell references. It makes it a bit easier. I can say this 0.82 minus, and then I can simply use the arrow keys and highlight my margin of error. You hit enter, and voila. For the right one, let me actually type in what we have here. We should have 0.82 for the p hat. And again, that's exact. So that's why I can just reference it in this way. Plus, I'm going to pull this margin of error because, again, I'm not exactly sure how many decimal places we need, or at least not just yet. One of the friendly things as you start to type these out, again, notice up top it gave me only 2 decimals. If you want more, highlighting up here, you can move either increase your decimals or decrease your decimals. And so I encourage you, when you're reading your situation, it's asking that you try to give it as many decimal places as it recommends. And 4 is our usual rule of thumb. Down here I have 5. Again, we could round it. I know this is going to round down, so it's going to stay at 2, or hey, I can just cut away a decimal place there as well. Again, that's up top for numbers. Now that we have our confidence intervals built, let me pull back up PowerPoint and I can write just like we typed. And there's your margin of error that we computed, 0.0235. And so when actually constructing that interval, well, we could write it very explicitly, just like we typed it. You had your left and your right endpoint, and that's what we're going to enter in for our left endpoint, 0.7965, and for our right endpoint, 0.8435. And there's our confidence interval built. In order to conceptualize this, I would encourage you to think about these in terms of the percentages that they represent. For instance, on my low end, if I routed that just to 2 decimal places, or better yet, a whole percent, that would be 80% of people will support a mandatory quarantine, or at least in New York. And if I look on the high end, it looks roughly like 84%. So here's how we can apply this. Certainly the firm would take this, and this is like bare minimum information, but they can actually more properly quantify the number of people. And that's what this next application is all about. The CDC confirmed the first case of Ebola in Texas, USA on September 2014. It's been a while. The New York population in 2014 was approximately that 6,350,802 adults. The question is, what is the lowest number of adults in New York who support mandatory quarantines with 95% confidence? Again, they're asking, like, what's the lowest number? Like, if we can't somehow get this passed, how many people are we, quote unquote, upsetting with their mandatory policy that they want to project? I have N times P, the number of people in this case doing what we are interested in. Lowest is what we're trying to project here. So it should be 6,350,802 times P by proportion. You can either use 80%. I'll be more exact and use the decimal that I have over here, 0.7965. And we should get a pretty large number. It looks like 5,058,413.8. Of course, you might be tempted to leave that alone. Please don't. Please make sure you round, because we can't somehow talk to 0.8 of a person, or at least I don't think we'd want to. I can round this to 5,058,414 New Yorkers, or I'll call them people. And so these policymakers, they want to know, look, how popular is this opinion? Again, they can wash their hands and say, look, we did what the people wanted what the people wanted us to do. And it looks like from our sample of 1,050 New York adults, after a little bit of normal distribution, again, keeping that margin of error, getting our best guess, it looks like on the low end, out of the 6 million people in New York, 5 million of them support this mandatory quarantine, using math to make that prediction. Did not talk to everybody, but I can certainly tell you on the low end, with 95% confidence, how these people feel. Next example. A survey of 349 randomly selected students at one university found that 302 students think that there is not enough parking on campus. Classic. Find the 90% confidence interval for the proportion of students at this university who think that there is not enough parking on campus. Again, these 349 people are anecdotal, right? 302 people's opinion doesn't necessarily hold much weight, but if we can project that onto everyone, well, then we can say, look, this is the very popular opinion. This is the proper proportion of people who think that there should be a change. As a side note, we'll write our answers as percentages, something like, let's say 35%. So first task, estimate the proportion of students who think that there is not enough parking on campus. We'll start with the classic formula. We're talking about sample proportion. It's X, the number of people who are doing what you want them to do, divided by N. There are 302 those individuals who agree with us, not enough parking on campus, out of the 349. As a decimal, that's 0.8653. If we have to round to a whole percent, in this case 2 decimals, we'll have to round that 5 up, and this is going to be 87%. And you can box that. That's the answer we're looking for. So things are kind of looking up for us, that's our projected proportion. And so again, the layman would just look at that and say, hey, look, this is what everybody thinks, but we know better. We know ideally this should be close to the population proportion P. But how close? Let's figure it out. Construct the confidence interval for the true population proportion. I got Excel open. This will help us out. Again, whenever you hear confidence interval, think, okay, I know how to make these things. It's going to be my sample proportion minus my margin of error, my sample proportion plus my margin of error, where I both have a left endpoint and a right endpoint to compute. I know what the sample proportion is. We just computed it, but I need to compute what that margin of error is as well. Again, in order to do that, there is a formula I could use, or I can just rely on the sweet, sweet old Excel and use this margin of error. So how do we compute it? It was equal, if you'll remember, confidence dot norm, and I had 3 inputs to put in, 1, 2, and that should be enough room, 3. The first one was alpha, or 1 minus my level of confidence. I have it circled up here. I want to be 90% confident, so I'll write 1 minus 0.9. Leave it against like a decimal. The second was a square root business. Again, you can just write square root. If you want to be really fancy, you can actually write the Excel function squirt. Don't have to. We'll be extra today. So squirt, and then I need p hat, 1 minus p hat. So I can write that as 0.87 times 1 minus 0.87. And that's our second ingredient. I'm going to have to move this 3 over, though, because we didn't quite fit it. And then that last input, the third one, is just the sample size. How many people did we talk to? That was 349. Shoo! But those are ingredients. And it's with those that we could very quickly, and you can check to make sure, you should get the margin of error 0.0301. Or as a percentage, because that's what we're dealing with here, whole percent, it says it's 3%. Look at that mirror image. Epsilon, Greek character E for error usually, and 3%. Let's build this interval. So for my sample proportion, that was 87% that we talked about earlier, minus my margin of error of 3%. You subtract those two, you should get 84%. For the right, the larger one, 87 plus 3%, you'll get something like 90%. So here are my 2 left and right endpoints, 84% and 90%. And that's the numbers that we're going to project out. Again, as low as 84 and as high as 90. If you want the actual decimal answers for 4 decimal places, I have them typed up there for you. So now we're thinking we have our confidence interval. Let's start projecting this information. Not so fast. We're going to run into a pickle. Let me show you. The university neglects to address their overflowing parking lots. Before issuing a protest, right, because we're upset, the student council wants to verify that they have at least 85% support. So question for us, can you guarantee with 90% certainty that the population proportion P is greater than or at least 85%? In fact, we are 90% confident that the population proportion is somewhere inside of this interval, the interval that we had 84% all the way to 90%. So I mean, at least 80%, it could be 90%. Wouldn't that be nice for our cause? But unfortunately for us, can we guarantee? No. Because again, it's possible that the proportion of support for not enough parking, it's possible that it's 84%, which for us is no bueno. So nope, we cannot make that claim. And so you might be thinking, well, then we're done here. There's a couple different things we could do. Maybe I take another sample, right? This is just the one that I got. N is equal to 349. But that's not guaranteed to work. Instead, let's seek of a different strategy to somehow that we can either bolster our ranks here, get a more accurate prediction. And that's exactly what we'll look into here. This next part is a little extra. And so if you'd like to skip it, you're like, look, I don't need the motivation. You're fine to move on. But for the rest of us, I'd encourage you to stick around and understand why we need this sample size, or why we need to figure out a proper sample size. So remember, our interval was from 84 to 90%. This is our, we'll call it our old interval. You'll see why in a minute. And the problem was our interval was too wide, because if I could somehow shrink it, well, then I'd have a proper interval that would guarantee that at least 85%. Well, there's only a couple things that we can control. I mean, I could control my level of confidence. I could say, let's bump down that level of confidence. That would narrow my interval. But then what does my interval really mean? It's not that meaningful. For instance, if I bumped it down to, look, I'm 50% confident in my interval, well, nobody's going to pay that any mind. In fact, as a rule of thumb, little side note here, 95% is the level of confidence that's kind of normally expected in any kind of publication. So what we can do in order to build a proper interval is I could just say, well, you know what? We were unlucky that time. Let me just get another sample of the same size. If I did, again, if I gathered the same sample size, 349, I may end up with a different, not nice proportion. Say maybe I end up with 85%. Well, I'm going to have the same margin of error because, again, that's based on my overall population information, in which case, look at that, I have an interval, it doesn't help me whatsoever. So a better way to do it is actually to choose our sample size instead. And what we'll do is we'll look at this formula that I mentioned earlier, the long-winded way. This is the critical value times your standard error value. And if we look inside of this formula, there's a pesky little n in there. It takes a little bit of algebra, a little bit of math, but if you solve this equation for n equals, you'll end up with something very special. You'll end up with a formula that'll help you choose sample size for confidence intervals. You need a couple ingredients to make this work. That's what's highlighted in this example above, but chance to say I'll just highlight what those ingredients are for the formula. So look, this formula is on a formula sheet for you. It's going to look something like this, right here. So you can take that for granted. The same formula that's written up here. But it's going to require the use of this table I have below. So let me really quickly go over the components of the formula. I would encourage you to notate what each term is, and that way we'll better understand what ingredients we're dealing with. For these two ingredients, these are the proportions that we're interested in. Sometimes the sample proportion, as we'll see in other examples, sometimes it's population proportion. Up top, this is that critical value we spoke of. This is just based on your level of confidence, beta. And so once you know what beta is, the classic example is 0.95. Well, you can go to your table. That would correspond to this column. And that would give you that your critical value, Z alpha over 2, is equal to 1.96. Again, always just based on the level of confidence. And then E, well, E is what it always is. This is your margin of error, or as I like to call it, your swing. How wide do you want your interval to be? So if you have these three ingredients, your proportion, your level of confidence, and your margin of error, you can figure out how many people you need to talk to in order to generate the confidence interval of your dreams, which is why this is always a nice place to start the conversation as opposed to backtrack when we have an interval that doesn't give us the results that we want. Speaking of an interval that gave us something we didn't want, if we remember that example we talked earlier with the who supports that we don't have enough parking, this is our confidence interval. And this was our old sample size, 349. Well, again, I got a margin of error that I didn't like. It was 3%. We couldn't do anything with my margin of error of 3%. It gave us a too wide of a confidence interval. I couldn't make an inference that I wanted to. And so instead, let's take back to the drawing board and ask this question. A university wants to understand the percentage of students who think that there's not enough parking on campus. In an earlier study, the proportion was estimated to be 0.865 or 87% like we rounded. How large a sample would be required in order to estimate the proportion at the 90% confidence level at an error, is a fancy word for us, error of at most 0.01 or 1%. This error 1% is going to replace our error of 3%. I want a very accurate, narrow confidence interval. Here's a little trick. How large of a sample? Well, they're asking us how large of a sample are we going to need? Then I'll start off with our formula first and foremost. Formula, it looks like this. N is equal to, I have P 1 minus P, and then I have my critical value, Z alpha over 2, divided by E, and this is the quantity being squared. So again, first thing, let's write the formula, then we can figure out what goes where. The first ingredient that I want to highlight for you is this population proportion. This is an old estimation, what we think it is, and so that's what I'll type in for the p-value. It should be 0.865 times 1 minus 0.865. And then here's my bigger parenthesis because I got a little division to go on under here. The critical value is a bit tricky, but again, it's always based on the level of confidence beta. It says up there I have a 90% level of confidence. Well, if I look, I can pull it from a table. 90% confidence. In fact, let me back up one so we can easily reference the table. In fact, here it is over here. 90% confidence, that should give me a critical value down below here at 1.645. So again, whenever you're looking at a critical value, look at a table and you can pull it from. There's a formula as well, but table is a little bit more friendly. So my critical value that I should be writing in there is 1.645, again, based on the beta value, 1.645. Beautiful. For the margin of error, again, this is your swing, and they want an error or a swing of at most 0.01. Let's make sure we keep it as a decimal, 0.01. Now look, a little bit of hand waving. I'll simplify it just a little bit for us to make the numbers a little bit easier to type in. This should be 0.865 times, if you do 1 minus, this should leave you with 0.135 times. This one isn't too pretty to do with either, but I encourage you to type it all in, 1.645 divided by 0.01 squared. And you should end up with a relatively acceptable number of 3,159.98. Ooh, we're so close. You might be tempted to box it. Please do not. We're not going to talk to 0.98 of a person. Let's always make sure we round up. And interestingly enough, this actually is a rule of thumb that you don't just round to the nearest integer. You always round sample size up. So this should be 3,160 individuals. That's how large of a sample I need. So again, before I talked to 349 people, that wasn't nearly good enough. I need to talk to many more people in order to get a very narrow confidence interval. So then again, you might say, well, then why do they only talk to 300 people? It's cheap. It's much cheaper to talk to fewer people. Unfortunately, that save comes with caveats, comes with that wider confidence interval, which again, may not give us the interval we're interested in. To wrap this story up in a bow, I have for you down here, check out that new confidence interval with that proper sample size. This is just Excel. I've typed out a little bit that sample proportion. Say maybe we got the same portion from the larger sample. Then my margin of error using that confidence.norm with my alpha, my square root business, and then my brand new sample size. In fact, I'll write it over here. There it is. Sample size. I will get, look at this confidence interval, 0.855 all the way to 0.875. And so if I was to write that confidence interval, and again, we'll round for simplicity's sake, that will be 86% all the way to 88%, or a margin of error of 1%. And so the beauty of this is, remember, we didn't want to protest or we didn't want to push the issue if we didn't have enough support, and it said at least 85%, at least, right? Well, we certainly have that. In fact, I can tell you the smallest I can imagine the proportion being is 86%. And so then we can go to the drawing board, it may be more. But again, one thing that's very important that we should understand is that at least 85% is only being claimed with 90% confidence. So there is a chance that I'm like, yep, I'll put my name behind it. We have at least 85%. And then when it actually comes down to it, when we actually talk to everyone, I was wrong. And so that's why that level of confidence, in this case 90%, is a very important little caveat, a little asterisk next to what you're building. Let's look at a confidence interval, but let's start with the good part of, look, how many people should I talk to? And that's what this example starts with. The State Education Commission wants to estimate the proportion of high school students in a state who read at or below their grade level. The Commissioner of Education believes that the proportion is around 21% or 0.21. This is how we'll start. How large a sample would be required to estimate the proportion of all high schoolers in the state who read at or below their grade level with 95% level of confidence and an error of at most 4%? How large a sample? All right, whenever they're asking for sample size, we got one formula for that. So right here, formula, n is equal to p, 1 minus p, yes. I then have z alpha over 2, all divided by my margin of error. And again, that's straight formula sheet to pull from. So I have a couple ingredients, in fact 3 to pull from, but all of them are given to me very fortunately. I'll write here equals. For the proportion, for p that they're estimating, that's this number, this 21%. Believes that the proportion is around 21%. So right here, 0.21, and then times 1 minus 0.21. You bigger brackets, let's start that quotient. For the critical value, again, this critical value is always based on your level of confidence, 0.95. And then what you're going to want to do is look at the table. If you use the table enough, you start to memorize them. You do not need to memorize them. Instead, go back to the table and you'll see it should be 1.96 is the number that we should get for the critical value. This 0.95 is the most common level of confidence. And so this one sometimes you'll memorize by accident because you use it so often. Maybe that might be too optimistic, but you can look at the table and pull it out, 1.96. Don't be fooled with this one. There's a trap. We need to write the margin of error. You might be tempted to write 4 here. Please do not do that, because this is a percentage, and so we need to convert it to a decimal. This should be 0.04. That's much better. And so when I plug all this in, again, multiply, make sure you divide, then square, then multiply. It'll take a little bit of time. You should get 398.3. You might be tempted to box that. Please do not. In fact, as a rule of thumb, you might be tempted to round down, but don't. Instead, with confidence intervals, we always round up. Always round up. It should be 399. That's how large of a sample we would recommend. Hopefully they took our recommendation. In fact, in part B, it looks like they did. Suppose a sample of minimum size is chosen. Of these students, 160 read at or below their grade level. Using this information, compute the sample proportion p hat, and we'll round to just 2 decimals. All right, no problem. P hat is equal to always x divided by n. Start off with the formula. It looks like I had 160 individuals doing what we were interested in this case reading at or below grade level. And so I can write that over my sample size of 399. As a decimal, it should be 0.4010, or in this case, they want me to round to 2 decimals. I can do that, 0.40. Or as a percentage, I can look at that at 40% are reading at or below a grade level. Again, at a grade level is perfectly fine, below is not, but that means that 60% of students, are reading above their grade level. That's a great thing. Here's our first application. Does your sample proportion, phat, conflict with your work in part A? Again, part A was that sample size information we did. What's that mean, conflict? Notice here proportion, it's read at 40%, but what proportion did we use? 0.21, 20%. So do they conflict? Yeah, they're different. So they said, hey, look, we think it's around 21%, take it or leave it. Well, in actuality, you were pretty darn off. And so, all right, proportion old was equal to 21%, which is not anywhere close to our sample proportion that we computed of 40%. And what that means is if I was to build a confidence interval based on this information, it's not going to have that same margin of error, that 4%. In fact, it's probably going to be more dramatic because I didn't talk to enough people. I should have changed this proportion to 0.4. But again, we didn't find that out until after I talked to those people. So a little too late for that. Last example. In a recent survey of 875 randomly selected U.S. adults, 243 said that their favorite sport to watch was football, and that's American football. We'll leave our answers as whole percentages, something like 45%. Let's dive in. First, let's start off with this sample they talked about. 875 adults, 243 of them said that their favorite sport to watch was football. Let's calculate a sample proportion. Here we go. phat is equal to x divided by n, no problem. 243 people doing what we want them to do, divided by that 875. We should get a decimal. It's repeating, but that's okay, of 2.777. They want us to leave our answer as whole percentages, so I'll write this as 28%. Now we'd like to say, okay, well then this is how the whole population feels, but I can't apply it just yet. In fact, really, if we were going to be rigorous, I should make that check that we did before, where I'm checking if n times p greater than or equal to 10 and n times 1 minus p is greater than or equal to 10 before you start building your confidence interval. But once we accept that this thing is approximately normal, we can certainly get into building it. Find a 90% CI, or confidence interval, for the population portion of U.S. adults whose favorite sport to watch is football. Here we go. Whenever you hear confidence interval, I'd encourage you to draw out what the reference is here. They're looking at phat minus my margin of error, phat plus my margin of error, where this is your left endpoint and this is your right endpoint. I should get an answer like, look, that left endpoint is going to be phat minus my margin of error. I know what my sample proportion is. That was that 28%. Ooh, I don't have my margin of error yet. That's okay. Let's compute it. Write it like we would type it in order to get it. Here we go. 28% for that sample proportion. So up top, I need to start off with that margin of error. Again, here it is for our reference. So we already have it. We just need to know how we would actually compute it. So it should look like this. Equals confidence.norm. And then I have the following three ingredients to type in here. Would be ample space for me. The first one is alpha, or 1 minus our level of confidence. In this case, we're building a 90% confidence interval. So I'll just write 1 minus 0.9 there. Or if you want to be fancy, you can write 0.1 is perfectly acceptable as well. For my second ingredient, you can write square root if you'd like to, or if you want to be a little bit more rigorous, inside of Excel, you would type in squirt. So that's what I'll do here. Again, you can write square root perfectly fine. And then I need my sample proportion here. Since we're writing 2.8, I'll write the same here. 0.28 times 1 minus 0.28. And that's our formula for the second ingredient. And the last one, our very favorite, is n, our sample size. In this case, that was 875. And with those three ingredients, provided that we have the equal sign here and confidence.norm, we'll get our margin of error, no problem, of 0.0249. How goofy that when you round this to 2 decimal places or a whole percent, you end up with minus 2% and plus 2%. Just to make the numbers work out nicely. Let's write that in our answer over here, that if I subtract, I end up with 26%. And when I add, I end up with 30%. That these is my confidence interval. Now look, my sample was anecdotal at best. I know it's close to the population proportion. How close? Well, it's like plus or minus 2%. And this is what I can project onto the group. Now look, maybe you're building this confidence interval and you project it, you give it to your boss and they're like, look, 90%, come on, get out of Little League here. And let's look at a 99% confidence interval. So somebody did it for us. A 99.99% confidence interval for the population proportion is 0.221, that's the low end, 22%, all the way to 0.334, that's 33%. What can you claim is the highest population percentage of adults who claim football is their favorite sport? Well, the highest one I can imagine is going to be that right endpoint, which is 0.334, or they want a percentage, and so I'll write it as 33%. Oh, you're feeling good about yourself, all right? But here's where we get into the application part. Let's see what we can do with that 33%. In years prior, an advertising banner costs around $750, let's say, but a marketing agent is now asking for $1,000. Oh, they're hiking the price up on you. The agent explains that in prior years, only 24% of U.S. adults' favorite sport to watch was football. Not very much. But a recent survey by their company showed that the percentage is now 35. They're like, look, this sport is growing. We have more eyeballs watching the sport. We're going to charge you more for your banner. So the question is, should your company pay the $1,000 fee for the banner, or do you suspect the agent is misleading you? Justify your response. So again, they're like, look, business is business, all right? It used to be 24%, now it's 35%. We got to start charging more, okay? Otherwise, we're going to get different advertisers. Forget about it. But we're looking at this 35% number. Again, right here, their claim, with, again, no level of confidence, I'm not saying anything over here, is that the proportion of people who enjoy football watching it is 35%. But we actually, I don't know if I agree with that. In fact, it looks like this number is a little bit off, because the highest we can imagine that proportion being, well, that's what we did in part C, is 33%. Not only do I think the highest it could be is 33%, I can say that with a lot of confidence. In fact, I can say that with 99.99% confidence. And again, all that means is that interval that I'm generating, intervals built in this way have a 99.99% chance of containing the mean. So in fact, when I say highest, I do mean that's the highest I can imagine being. It's equally likely that it's 22%, that it's lower than what it was in the past. So I'm like, hey, benefit of the doubt, the highest I can imagine it being, at least with my confidence interval, is 33. It could even be lower than what it's been in the past. But certainly, I'm suspecting that these people are misleading us. So should your company pay? The answer is no. We are not going to pay that $1,000. Instead, we're like, look, we've done the research. I'm trying to give you the benefit of the doubt that it's higher. But in fact, my confidence interval, the 99.91, is giving me wacky results where it can be as low as 22 and as high as 33. And again, this is why oftentimes you might be saying which one's better, this 99.99 or the 90. And I'll tell you, neither of them is. But really, the one we want is a 95% confidence interval. This is an industry standard, one that if we computed it, everybody goes, okay, look, that's what you got. That was your result. And then maybe some other university does a similar result. They'll also compute a 95%. And then you can compare apples to apples as opposed to this silly comparison of 90 to 99.99. Because what you notice is as that confidence interval grows, I went from 90 to 99.99. Look how huge that confidence interval is. It almost becomes nonsensical, where my highest is very high, 33, and my lowest is very low. It doesn't give me a proper inference. Look, let me wrap with this. When we talk about these confidence intervals, it's a best guess, right? It's like closing your eyes and picking a number. That's what sample are. It's random as we look around and pick a number, like let's say 28%. But it's with statistical certainty because we know the shape of the sample proportion. It's normally distributed. It's that little check that I referenced up above. That once I know this thing is normal, I can then project that onto a population because, again, I know how the population proportion is distributed over the sample proportion. And so as long as I make that prediction, and again, little caveat, all right, there's a 90% chance that this interval contains the mean. Well, then it's that blind guess, once I build a little bit of statistical work from, that I can make these bold claims, that we understand a population who we never talk to just based on a sample. So there's a couple caveats to keep in mind with these confidence intervals, but certainly the claims are valid in the way they're provided. Let me end with this. If you enjoyed the video, I appreciate the time you put into it. If you didn't, I apologize. For the rest of us, I'll see you in the next one.